All right, so let's recap a little bit where we are. Some important concepts we've talked about are groups, functions, symmetries. Okay, so let's see if we can tie these things together. We noticed that functions, symmetries are functions, and symmetries form groups. Right? Symmetries were a very special kind of functions that preserved the appearance of geometrical objects. But we can generalize somewhat. Let's consider any set of functions where the domain and the codomain are the same. I'm sorry, I shouldn't say any set of functions, any set of bijections where the domain and codomain are the same. Now, symmetries, they had to preserve distances and angles. We're going to relax that condition and say, well, any bijection where the codomain and the domain are the same. And we're going to call this type of function a permutation. Now, we're actually going to deal with finite sets and not infinite sets. So we're not going to talk about permutations of infinite sets. And here's the definition. A bijection whose domain and codomain are equal is called a permutation. The set of all bijections from a finite set X to itself is called the set of permutations on X and is denoted by Sx. So we are going to be talking about finite sets. That makes the writing a lot shorter. So in fact, any symmetry is a permutation. If you look at the equilateral triangle and the symmetries of the equilateral triangle, there were 6 of them. So these 6 symmetries give us 6 permutations. The question is, are there any others? Well, you can think about that question and discover that really those are the only 6 bijections from the set ABC to itself. If I just think abstractly of the bijections of ABC to itself, right? So we can show bijections using an arrow diagram. So if I just count up the possibilities, well, one possibility is A going to A. Then I can choose for B and C. I have a choice. Either B goes to C or C goes to B. So there's 2 there. Another possibility is A goes to B. And then for B and C, there are 2 possibilities. Either B goes to A, C goes to C, or B goes to C, C goes to A. All right? Or A goes to C. If A goes to C, you can see also there are 2 possibilities for how B and C can go. So if you count up all the possibilities that I've listed, you'll see there are in fact 6 possibilities for bijections from A, B, C to itself. Now that was the case of an equilateral triangle. If I looked at the symmetries in an isosceles triangle, you only get 2. It's a subset. Okay? So in fact, the set of symmetries is a subset of the set of permutations. Always a subset. Okay. Now we talked about how symmetries form a group. It's natural to ask the question, do permutations form a group? And in fact, they do. You have to show the different properties of a group. First of all, you have to show a closure. Okay, you have to show that the composition of any 2 permutations is also a permutation. And actually, that simply follows because permutations are bijections, and the composition of bijections are bijection. Next, you need to show that the permutations have an identity, and they do. They have the permutation that doesn't move anything. That's the identity. We need to show that any permutation has an inverse, and it does because we're talking about bijections again. And since functions are associative, we also have that permutations are associative. Okay, so we do have the permutations of any set X form a group under function composition. All right, so let's consider the permutation group on n objects. Now, you could list a set of n elements. You could say A, B, C, or 1, 2, 3, or you're really doing the same thing. You're just changing the labels that you're labeling the objects with. You're basically going to have the same mathematical structure. So, for instance, this makes a connection between permutations on the set A, B, C, D and the permutations on the set 1, 2, 3, 4. You can see actually that this permutation represents the same permutation as this one. This permutation represents the same permutation of this one. If I just change these A's and I cross them out, if I replace A with a label 1, B with a label 2, C with a label 3, C with a label 4, then here this D is 4, 3, 2, 1. All right, I'm getting the same thing as here. All right, so defining the number of elements in a set as the order of that set then if there are n elements in a set, the permutations on an n element set are virtually identified with the permutations on this set 1, 2, up to n. Okay, so we're going to use this as our standard representation for n elements, and we'll call the group of permutations on this set 1, 2, up to n as the symmetric group on n letters. Now, symmetric group doesn't mean it's a group of symmetries. Okay, it's not actually symmetries, so be a little bit careful about that notation. Symmetric group doesn't mean it's a group of symmetries. As we've seen, permutations are more general than symmetries. There are more permutations than there are symmetries. Symmetry refers to geometrical property. The symmetric group is just a purely algebraic notion. Okay, so here we're talking a little bit farther about the idea that these two groups, these two permutations, the ones with A, B, C, D, and the ones with 1, 2, 3, 4, are essentially the same. We've just done a relabeling of the permutations. This type of relationship is called isomorphism. Okay, so the point is that if I label n elements 1, 2, up to n, or if I label them A, B, C, and they both have the same number of elements, the corresponding groups on those elements are isomorphic. Right, so that makes the point again that it doesn't really matter what letters I use, I'm still getting the same group. Okay. Now, it's possible for a group to fit inside a group. We've talked about symmetries. Okay. Now, we mentioned that the symmetries of a triangle are in fact equal to S3. The set of permutations on three objects is the group of symmetries of an equilateral triangle. But if I take the symmetries of a isosceles triangle, there's only two of them. So the symmetries of an isosceles triangle are contained in S3. Now, the symmetries of an isosceles triangle do form a group. It's a group that's contained in another group. This is called a subgroup. Very key concept. Groups inside of groups. Now, any subgroup of the symmetric group is called a permutation group. Okay, so you take a symmetric group on n letters, take a subgroup, it's called a permutation group. Okay. And it turns out that to verify whether something is a subgroup, it's not so difficult as verifying whether something is a group, because subgroups have inherited properties from the group that contains it. For instance, if I want to show a subset of a group is a subgroup, I don't need to show associative, because any operation in the subset is also an operation in the big group. So any thing that I could write, say A, if I have something like this in the subgroup, I can also consider this as something in the group, so I know that this will hold automatically for any elements in the subgroup. Okay, so let's stop here. We'll get into some interesting representations of permutations in the next section.